Sully Elmer. I'm a biomedical engineering student, and I'm the team lead for this project.
I'm Paige Rudy. I'm a biomedical engineering student, and I'm the procurement lead.
I'm Ashley Wheeler. I'm a biomedical engineering student, and I'm the software lead.
I'm JC Miller. I'm a biosystems engineering student, and I'm the experimental lead.
I'm Farah El-Karaguli. I'm a chemical engineering student, and I'm the chemical lead.
And we're Team 2441.
JC, what was Team 2441 tasked with this year?
We were tasked with creating a device for high-throughput drug screening of agents targeting mechanically activated platelets.
Can you answer a couple questions about it?
Sure.
What are platelets?
Platelets are cell fragments in blood, and platelet activation causes blood coagulation after an injury.
What happens when platelets activate too much?
That can lead to thrombosis, which is blood clots getting stuck in blood vessels.
Is thrombosis bad?
Yes, because the blood clots can travel through your vessels to your heart and brain.
How can platelets be activated?
Biochemically or mechanically. Patients with CTDs experience excess mechanical platelet activation.
Why is Team 2441 trying to mechanically activate platelets?
Because shear-limiting drugs currently on the market only target biochemically activated platelets, and we want to allow lab technicians to assess the efficacy of drugs that target mechanically activated platelets.
Thanks. Let's go over some specifics of the system. There are two main components to the system, including the shear induction mechanism and the activation display. Starting with the former, the device consists of an Arduino Mega that interfaces with the user's laptop and device code, powering a DC motor through an L293D motor driver. Each motor is equipped with a neodymium drive magnet that induces rotation of the four magnetic bobbles suspended by ball bearings into the wells of the 96-well plate. When preparing to run the system, platelets are loaded into the wells using a handheld pipette, and the user will input RPM and run duration variables into the Arduino IDE code on the lab bench laptop. Testing is initiated by running the code. To read the level of platelet activation, the user should follow the steps of the platelet activation state or PASS assay, a colorimetric assay that JC will describe in a few minutes. At the end of this process, a plate reader will read the activation levels and the data can be exported as a TXT file. The data from multiple runs can be processed using the GUI, a MATLAB app. Users can input parameters including RPM, time, and positive or negative control readings. The app includes functionalities for loading raw data, normalizing and calculating raw and average activation levels, and saving manipulated data for further analysis. Now let's head over to the EDC to check in on Sully.
The EDC is where we fabricated the mechanical assembly of our Vibroshear system. Most of the physical components were manufactured through PLA 3D printing here. Let's take a close-up at each component. Here's a magnetic stir housing fit with the bottom piece containing slots for the motors and wired connections to a breadboard. To attach the neodymium drive magnet to the motor, an external piece was designed with a hole cut out to fit the output shaft of the motor, and this attachment piece contains a tightly tolerant open space to house the drive magnet. Here's what the motor magnet assembly looks like. Naturally, there's also a top component to enclose the housing with ridges along the corners of the top that securely carry the 96-well plate during the device's use. Outside of the housing, something has to respond to the drive magnets to impart shear in the fluid within the wells. That takes us to the spinning bobble piece, responsible for mechanically agitating platelets. After several prototypes, here's the final model used for the bobble, 3 discs stacked on top of each other with space between to trap the fluid within. In cylindrical shape to maximize surface area, ensuring abrasive collisions with the surface of the piece consistently. There are 4 of these bobbles embedded within the plate lid, and here's how the whole assembly comes together.
Hey Ashley, what are you working on?
I'm actually working on the electrical components of the Vibroshear system.
Oh wow, can I see more?
Yeah, let me show you. Alright, let's go into how we get this device up and running. To start, I want to note that a breadboard is used for simplicity reasons, but the actual solid board can be seen in the top left-hand corner. Now let's begin with the Arduino Mega, which is a component of the electrical system allowing for connection between the computer and motor for trial runs. For the Arduino, we have connections made to an L293D motor driver. What this motor driver does is control the DC motor. To do so, power from an external power source, in our case the Arduino, is supplied. Additionally, for communication between the motor and the computer, a total of 4 connections are made to allow for switching the motor on and off, as well as feed the voltage into it for speed control. Now let's move into a snippet of our code. In this code, you'll see that the connections are established at the beginning, and the only portion of the code that needs to be changed by the user is the duration of the delay, which corresponds to the duration of the trial. A user manual page is provided for the user's convenience on this to simplify the process in the final report. Lastly, if during a trial a user needs to stop the process by any means, they can simply type into the serial monitor 0 and the code will automatically stop, just in case there's any issue that may have risen during the trial.
Hey JC, where are you headed?
Oh, I'm actually headed to the lab to do some experiments. Let's go! After creating the reagents needed for the pass assay protocol, we need to create 20K GFP by diluting it with a platelet buffer. We then add chromozyme TH, which will slightly speed up platelet activation. Next, we'll fill the proper wells with our GFP solution and activate using the Vibroshear system. We then need to incubate our incubation solution in a water bath at 37 degrees Celsius. We'll add the activated platelets to this along with the reagent factor 10 and incubate again. After filling our read plate with the well solution, we'll transfer the activated platelet solution to the read area and finally read the plate.
Sarah, what's your favorite application to use?
I'm actually using it right now. Let me show you.
After the device is finished running, the user can export a TXT file from the plate reader with the raw data. In the Analyze tab, the application accepts parameters specific to the run, including runtime, RPM, and positive and negative control readings for normalization. The exported TXT file can be imported using the Load button, and for set activation calculated using the Generate button. The Average button calculates the average of the 3 replicates for each well and the grand average. All results for that run are returned to the results section. This process can be repeated for however many files the user likes. If the user makes a mistake, they can clear the most recent run or clear all. The Save button saves all the displayed data to a CSV file for further analysis.
Now, let's take a look at how we got to our final design.
Platelet activation levels of 70% or greater indicate that platelets are fully activated.
Techs in Slepian's lab usually use high-power machines to activate platelets for their testing.
We wanted to downscale this to a 96 well plate in order to be able to test a large amount of biological compounds at once.
We originally tested on a magnetic stirring device and got really low activation.
So we tried changing our independent variable to determine the most effective parameters for activation.
These variables included bobble design, runtime, volume of the wells and platelets, rotational speed, and adjusting the protocol with biochemical additives. Finally, we were able to get the perfect combination of these variables and determine the protocol for optimal platelet activation.
Now, knowing the whole project, we can briefly discuss the final results we received. On the right-hand side, you'll see an average of the trial runs with the final device. Due to constraints within the lab, the gold standard for 100% platelet activation was to use a chemical agonist known as calcium ionophores. That said, with the chemical agonist, 20% was considered fully activated for our testing purposes. Our data exceeded the gold standard, indicating that our device was successfully activating platelets in a mechanical manner.
With that, throughout the last 8 months, we've worked hard to create a proof of concept device that is aimed at generating mechanical shear onto platelets with an high throughput setting of a 96 well plate. Our product serves to pave the way for future research on drugs that limit mechanical platelet activation. Overall, we'd like to thank the Slepian Lab and our mentor Don McDonald for their support.